Okay, welcome back. So this is the second video in the series of some geometry lessons. This is the figure that I drew in the first video. It was showing how we can go from one line, which is the radius of this circle, then draw the diameter, move down the radius, create this triangle, two triangles, draw a bit of a circle to outline where we can make a golden rectangle. So here I'm just going to add this line to make it a complete golden rectangle. Also the line where this curve and the sides of the golden rectangle where they intersect, we can add a line there and then we get a square. So here we have a unit circle created from an arbitrary length. Of course I have chosen a length now, but you can choose any length. We have the unit square and also the unit golden rectangle, all having a relationship to the diameter of the circle. In this video I'm going to show how from here we can arrive at the proportions of the Great Pyramid, which is very interesting. So what I will do is I will draw how the pyramid might have been laid out, so we get the exact proportions. So we start from here. We have a golden rectangle, and when we have a golden rectangle, it's very easy to draw a Kepler triangle. We take the compass, we take the whole length of the long side of the golden rectangle, and we draw a curve. Well, I'm just going to pretend I'm drawing a curve. I don't want so much lines. So just down to here, and where this intersects with this, the other side of the golden rectangle. Now we have a Kepler triangle, like this. Now we have four figures, which is very interesting. We have a circle, we have a square, we have a golden rectangle, and also a Kepler triangle. And all share the diameter of the circle, including the circle, of course. We can say that the relationship between the circle and a square, we can say that is pi. We can say that the relationship between this square, now I'm talking area. The area of this circle compared with the area to this square can be said to be pi. The area of this square in relation to this big golden rectangle is phi, and also the square to the smaller golden rectangle is also phi. What's interesting is with the Kepler triangle, if we take here, we say this is the base of the Kepler triangle, this is the height. If we take the height of this Kepler triangle in relation to the circumference of this square, now I'm talking circumference because here we have a distance, a line, so then we have to compare it with the same, which is the circumference of the square. The circumference of this square, I have used this line, or the length of the diameter of the circle is 8 centimeters. So the circumference of this square is 32, 8 times 4. The length of the Kepler triangle of the height, I have calculated here. This is 8, and to get the height of the Kepler triangle, you take it times the root square of phi. So that's 10.176 and so on. If we take the circumference of the square divided by the height of this Kepler triangle, we will get a number which is 4 divided by root square of phi, 3.1446055. This is of course very close to pi. That is interesting. And we will also expand a little bit about this. I was talking about the pyramids, and I want to show you how we can get the proportions of the pyramid, the height to the base. So we say that the height of the Kepler triangle, that will be the height of the pyramid. So this is the height. Now what I'm gonna do, I have a square here. I'm gonna fourfold that square. So I'm gonna make 3 more. So I have 1 more square. I will quadruple it. So we do like this. I know the proportion. Here I have a square paper, which makes it much more easier for me to work on. So here I draw the 4, 6, 8. Okay, there we go. Here. There, and let's draw that last square now. Here it goes up a little bit to the numbers I have been written, but okay, doesn't really matter, it's more or less so like this. So here we have a base and we have a height here. Now, how do we get at the proportions of the Great Pyramid? We know that the height of the Great Pyramid is 280 cubits and the circumference of the base is 1,760. So what we can do from this drawing I'm doing is of course completely numberless. You can use any unit, any distance. So if we imagine that this first line, the radius that I make this unit circle, the start of this whole figure, if I put the value of 110 Egyptian cubits as the start of this radius, that will mean that the diameter is 220 cubits. This means that, of course, the diameter is equal to half of one of the sides. So then it's 2, so one side is 440. And if you take all 4 sides, 440 times 4, then you will arrive at 1760. And that is the base of the Great Pyramid, and 440 cubits is the side. Now, how do I arrive at the height? Well, as I said before, to calculate the relationship in a Kepler triangle is the base is 1, the height is root square of phi, and the hypotenuse is phi. So if I want the height, I need to take the base times the height. So in my proportion of 110 cubits as the starting line, I know that this side is 220. That equals to the base of the Kepler triangle. So to get this side, I need to take 220 times root square of phi. That I have done here, and that is shown to be 279.844322893, and so on. So this means that the height of this pyramid is 279.844 and so on. This is very close to the height of the Great Pyramid, which is said to be 280 Egyptian cubits, which of course is very, very difficult to tell from this number. It's almost the same. So this is a way how the pyramid might have been laid out. This also corresponds to squaring the circle, as we have the Kepler triangle here and this square here. So what I'm going to show now is that this circle that I will outline here really made for this kind of pen, but let's do it. Okay, there. So in this drawing, this big circle and these four squares, or as we call the base of the pyramid, they will be equal. Of course not if you're using, if we say that it's an approximation of squaring the circle, because we use the Kepler triangle, we know it's a very close approximation. But we can do it in another way. Now, if I would extend as I showed you before, that the height of this Kepler triangle, if we divide the height with the circumference of one of these squares, that will yield the number 3.144655 and so on, which is equal to 4 divided by root square of phi. If we instead take the diameter of this big circle, the length of the diameter divided by the circumference of this whole square is also 3.144655. Now, if we, for example, when they measured the Great Pyramid, they come to the approximation of 22 divided by 7. For example, if we would take this height as 280, which is an approximation, 280, and we take the circumference of this square, which is 880, so 880, let's have another so we see well. 880 divided by 280, that is 22 divided by 7. So in this drawing, 22 times 22 divided by 7 becomes an approximation of this number, because this is the number that pops out when we use this. And as you can see in this drawing, I do not put in any numbers. It is completely numberless. You choose yourself what number you want to start with. And the length of this starting line will decide all other relationships and all other numbers that come out. So that's very interesting. That's very interesting. So this is a numberless way of arriving at the proportion of the Great Pyramid, where the height of the Kepler triangle here is the height of the pyramid, and these four squares is the base. And the relationship of that comes out as 3.144. So that's, it points maybe to an idea that the Egyptians maybe saw this as pi.